All right, hey everybody, Dr. Powers here. I want to demonstrate this lab in STP420, this lab 2.4, which is looking at this statistical phenomenon, we'll call it, called Simpson's paradox. And it's really looking at what can happen when you have some factor underlying your data that has a influence that you're not really even aware of. Sometimes the apparent pattern in your data can completely disappear or be like reversed when you take into account some other data or factors. And this often happens when your data is aggregated as opposed to if you kind of break it down into pieces. So this lab is based on an actual case from 1973. There were I don't know the exact details, but I imagine there was an investigation into an accusation of gender discrimination in the acceptance rates of students at UC Berkeley, and the data we'll be generating is very close approximation of the data that was collected back then. And so we'll be looking at the patterns in the overall data set and then looking at how we can explain it and understand it by drilling down into the underlying kind of components. So here's the population. If you can just click on this link and it'll take you to this simulated population. We've got three variables that we are able to sample and look at. We have gender of applicant, the program they're applying to, and whether or not they're accepted. To start things off, we're just going to create a large sample, a sample of size 12,763, which is the same sample size that was collected back in 1973. Why did I? 12,763. Let's click sample. It takes a couple moments for it to be generated. We have all our data now. For this, it's going to make more sense. It's going to be easier to actually analyze all of this data using the data analysis kind of page that you can get to here. But first thing you want to do is save your data set. Save it as a CSV. I'm going to go to the datasets page, which I actually have open over here. And I'm going to choose the file from going to, it's done. It's up. Okay, so we have the data set here. We have three variables. We have 12,763 observations. Going to start by just doing a quick look at the acceptance rates by gender. So we have two variables, gender and accepted, and they both have two values. Their gender is male, female, and accepted is either accepted or rejected. If I look at a contingency table, this is a very fast way for me to take a look at the these proportions. And under the marginals table, you can get a quick little table. Rather than looking at the frequencies, I want to look at the row proportions. It'll tell me what the acceptance rates is for female and male applicants. So look at this. If we stop right here, we would say there's clear evidence that there is gender discrimination, right? It looks like the acceptance rate for female is only 28.6%, for males 46.6%. There's a very big difference, almost a 20 percentage point difference there. But that doesn't tell us the whole story, and this is where things get really interesting. What we're going to do is look at acceptance rates across those three programs. I'm going to go back here and pick the program and whether or not they're accepted. And I'm going to look at this breakdown for female students and for male students. Going to add a data filter, select the gender variable, and just select the male students. Create a contingency table, and that's going to show me the acceptance rates. I'm going to, now I'm going to look at the marginals table, and I'm going to convert these into row proportions. We can see here which of the programs have the higher and lower acceptance rates for males. Looks like for males, we have like a 65% acceptance rates for program A. For B, it's like 61.5%, 36.3%. You can see the acceptance rates going down and down and down as you go through programs A, B, C, D, E, and F. Okay, what we really are interested in doing is comparing those acceptance rates to the acceptance rates for the female applicants. Do that now. I'm going to go back here, choose female as the filtered value, and create another contingency table. These are the accepted, rejected for only the female applicants. And I'm going to again look at these row proportions in the marginal table. Let's look at row proportions and compare those to the male students. And you'll see, putting them side by side, and I'll put it like that. It looks like the acceptance rates are comparable. It looks like they're a little bit less for program A. It's actually a little less for program B. And C, it's pretty close for D. It's a little higher for E, and it's just a tiny bit lower for F. But notice none of those differences are as huge as we saw in the initial comparison, right? We saw a difference of about 20 percentage points. Here, this is what? 4 percentage points. This is like 4 percentage point difference. This, like 3 percentage points. This is like half, like not even 1 percentage point difference. And then this is higher by a half. This is less than a half percentage point. Yeah, so how is it possible that when you aggregate the data, you get this large difference between the two? Well, the answer comes from looking at the programs themselves and who is applying to them. I'm going to close both of these, and I want to just take a look across the board without filtering by gender. What is the acceptance rates for each of these programs? So this is for all 12,000 applicants. Looking at the acceptance rates, I'm going to just look at row proportions again, and you can see that the same pattern is here, right, where we have a higher acceptance rates for program A and B, and then it goes down for programs C, D, E, and F. The acceptance rates dip down. If we look at a chart, that would really show us, this is not a good way. I have to transpose my data to really look at this properly. Here we go. By program, the acceptance rates, you can see that A and B have a very high acceptance rate, C and D much lower, and then E and F are highly competitive. Why does this matter? Well, we want to look at what programs, the proportion, the gender proportion of applicants for each program. So I'm going to ignore the accepted variable at the moment and just look at the program by gender and take a look at, let's see, I think that it's going to be easier for me to, well, let's just make this bigger. We can look at the whole thing. I'm going to look at the proportions first. I guess here we're going to look at the column proportions. And this is where we can see an explanation of why this pattern's emerging. Programs A and B, you can see the vast majority of applicants are male, right? We have 88, 89% almost for program A, 95, 96% for program B. Those two programs have a much higher acceptance rate, and that means we're getting a lot more males accepted to the university as a whole. For C and D, well, let's see, C, we have a higher proportion of females. E and F, higher proportion of females. D is pretty similar between males and females. So what we see then is the programs with lower acceptance rates are higher proportion female applicants. That means that we're going to be getting, more of the female applicants are going to be getting rejection letters because of the programs that they're applying to. Now, I don't know exactly what programs A, B, C, D, E, and F exactly were, but there's any number of reasons why there could be a difference in application kind of proportion between these two programs, or these 6 programs. But the important thing to realize here is this, we've kind of uncovered the explanation of this apparent pattern in the aggregated data. It disappears, or in some cases it disappeared, but in a lot of cases it's much, much lessened when we break it down by program. So the interaction between these 3 variables creates this pattern between gender and acceptance rate. This is Simpson's paradox in a nutshell. It's when when one pattern in the data can be explained when you kind of break it down into different perspectives. Okay, but that's all I want to cover here. I hope this demonstration is helpful for you, and I will make another one of these soon. Okay, bye.